Hello, I'm Sonia Majzoub, a marketing executive at Eland Cables. At Eland, quality is paramount. We aim to bring you the highest standards in engineering when it comes to the cables we sell. And it was with this in mind that we chose to undertake the spike test as specifically required by Network Rail on samples of 33 kilovolt cable. A spike test is a test designed to prove that the copper wire screen can withstand a full specified fault current of 3 kiloamps for a period of no less than 3 seconds. It simulates the accidental spiking of a live cable installation.
The test was carried out at the prestigious independent CESI facility in Milan, which is one of the only facilities in Europe with the capability of conducting such tests. Prior to the test itself, the samples of cable underwent a thorough process of preparation, which was overseen and verified by the Eland Cables technical team, as well as by a Network Rail senior on-site project engineer. What does this mean in practice? To begin with, the heavily graphited MDPE sheath was stripped back 600 mm to reveal the water-blocking tape. The equalizing tape was removed, before which the copper screen was formed into a pigtail to ensure optimum connectivity during the test. The bedding tape was unwound, uncovering the insulation screen, or semiconducting layer. This was verified as banana strippable by the Network Rail test witness and by another client. The insulation was then exposed, the end of which was carefully measured to the required 70 mm. This was then removed by the standard stripping tool used by Network Rail jointers. The insulation and semiconducting screen came off cleanly, finally to expose the conductor. A lug was fitted to the end and then crimped in place using a newly calibrated hydraulic crimping tool, which was fitted with inserts of the correct size. This ensured that the lug was securely attached to the cable. The cable was now fully prepared and ready for testing. Given the high amounts of electricity used in the test, careful preparation of the site needed to be carried out to ensure both the accuracy of the test and the safety of the team. The phase conductor was connected to a single-phase 50 Hz power supply and the pigtail connected to earth. With the connections made, a spike of the prescribed diameter was driven into the center of the cable sample to ensure contact with both the copper wire screen and with the phase conductor. Once verification of the short circuit between the copper wire screen and the phase conductor was confirmed, the cable was then declared ready for testing, and the team withdrew to the safety of the observation bunker. Final calibration checks were performed, after which the test was ready to be initiated under the observation of the witnessing team from a safe distance. Even at the distance of approximately 150 feet, the visual spectacle clearly demonstrated the potential danger that could result from a real-life situation. For a more detailed look at what happened, here is the same test viewed through a shielded high-speed camera which was installed approximately 2 meters from the cable. Shot at high speed, the first second of real time is shown in slow motion to enable the process to be more clearly visible. In this first second, it is possible to see how the gases were vented around the spike as the arc was struck. The pulsation visible in the arc was the alternating current flow through the phase conductor down to earth. The arc reached approximately 1,500 degrees Celsius in 0.2 seconds. The arc systematically burnt the outer sheath, the copper wire screen, and all layers down to the phase conductor. Here you can see the remains of the steel spike melted into what was left of the conductor. Despite this expected damage, the cable was able to sustain the fault current of 3 kiloamps from phase to earth for more than 3 seconds, which fulfill the requirements of the Network Rail specifications.